Super. Herzlich willkommen zum 2024 YSP Award. Die Bude ist voll am BFW. Im Web sind auch einige dabei. Herzlich willkommen zu dieser Ausgabe. Wir freuen uns wahnsinnig. Ich glaube, man kann die Aufregung im Raum schon förmlich spüren. Matthias, was erwartet uns heute?
Ja, wir haben heute die Finalistinnen da vom heurigen YSP Young Snow Professional Award. Und ja, da geht es heute darum zu schauen, wen wir küren und wen wir zu den unterschiedlichen Veranstaltungen schicken. Welche Veranstaltungen sind das, Christoph?
Es gibt 3 Veranstaltungen, die wieder unsere jungen Professionisten aus dem Schnee- und Lawinenbereich hosten werden. Das ist das Alpinforum. Das ist das DCNA, unsere strategischen Partner sind dabei. Groß an Mathe Knaus, herzlich willkommen hier, schön, dass du da bist. Und natürlich an den ISSW 2024, also International Snow Science Workshop, der diesmal in Tromsø, also in Norwegen, stattfinden wird.
Und deswegen machen wir das Ganze auch in Englisch heute, zumindest die Vorträge danach sind in Englisch. Das ist also der Grund, internationale Konferenzen, deswegen werden wir uns anschauen, wie unsere Finalistinnen in Englisch vortragen können. Ganz kurz noch, zu der Folie. Und zwar unten sind die Premium-Partner und die Partner, das will ich deswegen erwähnen, weil mit diesen Awards natürlich ein bisschen Geld, eine Unterstützung für unsere YSP-Gewinner dann mit einhergeht. Und ohne diese Premium-Partner und Partner funktioniert das also nicht. Premium-Partner mit Wissen Avalanche Control, was schon seit Anfang an dabei sein und uns unterstützen. Orthovox, Open Faces, Alpenverein und neu dazugekommen ist SIL. Unsere Partner Lola, Synalp und Alpinfra, eben das sind sehr, sehr wichtig, damit wir das überhaupt machen können. Und vor allem auch ein sehr großer Teil von unserer finanziellen Mittel kommt von Mitgliedern. Das ist ja oft zu unterschätzen, weil es natürlich ein kleiner Beitrag für jeden ist, aber in der Summe ermöglicht uns das eben auch unsere jungen Forscherinnen und Forscher und Praktiker zu unterstützen.
Ja, von Anfang an dabei 2 große Unterstützer, denen wir diesen Award gewidmet haben. Also Charly-Sam, ehemaliger Institutsleiter vom BFW, und Sam Wissen, die diese Organisation von der ersten Stunde unterstützt haben und die leider eben nicht mehr unter uns sein können, um diese wunderschönen Themen, die wir jährlich hier besprechen, miterleben zu können, aber trotzdem im Gedenken an ihre Haltung, an ihre Attitude, wie man so schön sagt, ist dieser Award gewidmet, und vielen Dank an die 2 für ihre Unterstützung seit jeher.
Ja, wie läuft das heute ab? Wir haben diese 3 Finalistinnen, die ihren Themenbereich oder ihre Themen bei uns vorstellen. Englische Sprache habe ich schon gesagt. Jeder der 3 Finalisten hat 10 Minuten Zeit plus 3 Minuten Diskussion. Und in weiterer Folge, wie auch vergangenes Jahr, gibt es eine Beurteilung dieser 3 Präsentationen. Einmal inhaltlich, einmal Präsentation und danach die Expertise, die was in der Diskussion gezeigt wird. Also das kann beurteilt werden und sollte, also wahrscheinlich ein Aufruf an alle, die was da zuhören, an diesem Seminar, dass sie bitte da mitmachen. Das ist der QR-Code, den werden wir später nach den Präsentationen nochmal sagen. Das könnt ihr jetzt währenddessen machen und beurteilen. Das könnt ihr aber alle 3 auch im Nachgang beurteilen. Ja, vielleicht könnt ihr das eigentlich schon einmal den Link holen, den werden wir danach auch im Chat auf YouTube und auf Zoom instellen. Auch die Beurteilung folgt dann eigentlich so, dass es hat ja schon eine Vorauswahl gegeben von diesen Leuten, die ihren Beitrag eingereicht haben. Da hat es einen Review-Prozess gegeben, deswegen sind diese 3 dann ausgewählt worden aus diesem Review-Prozess. Da ist dann vor allem um den Inhalt gegangen und um das Abstract, das eingereicht worden ist. Also dieser Teil der Beurteilung fließt dann am Ende auch ein. Ein zweiter Teil der Beurteilung ist der Review, den was S-Hind macht. Und schlussendlich nachher auch gibt es ein Gremium von der OEGSL, das was den 3. Teil darstellt. Und dann in den nächsten Tagen wird eben verkündet, wer gewonnen hat. Gewinnen werden alle drei, haben wir
Das
schon
ist
erfahren.
cool, ja.
Aber wer noch dran so kommt, dafür ist sicherlich die spannende Frage dann, die was wir in der nächsten Tage klären werden.
Das Podium wird in den nächsten Tagen verkündet, also es bleibt dann noch ein bisschen spannend, auch diese Präsentierenden. Und ja, ich denke, wenn es keine Fragen mehr zur Evaluierung gibt oder auch von euch, starten wir los.
Medias Res.
Genau. Und bitte, Matthias, wenn du die erste Einführung könntest, danke.
Ja, ich werde kurz machen. Die Andrea Bruckmeier hat ihre Masterarbeit am Institut für Geografie an der Uni Innsbruck gemacht. Hat er jetzt erfolgreich abgeschlossen. Ist auch in der Bergwacht in Bayern tätig, in diesem Schnee- und Lawinenbereich mittlerweile schon sehr gut angekommen, sehr interessiert, sehr motiviert und wir sind jetzt sehr gespannt auf deine Präsentation.
I will switch to English now. And it's a great honor to be here and to present in front of this audience. Thank you for that. And I think I need to switch the presentation somehow. So sorry for this delay, but so I will start now. Yesterday, when I looked out of my window, I saw this beautiful picture and I saw some wet snow avalanches just right above Innsbruck. And I thought about when I was thinking about this topic 2 years ago, because researchers like you, Christoph, pointed out that wet snow avalanches are quite challenging to forecast and to predict. So we thought about how is it, or is there an opportunity to somehow contribute to facilitate the forecast with openAMUNDSEN, snow modulation, or is there somehow a possibility to contribute to the determination of the wet snow avalanche problem? And this was actually the basis of my master thesis with the title openAMUNDSEN Snow Simulations for the Schober Mountains and DefereggerAlps for the winter season 1920 and 2021 to support the determination of the wet snow avalanche problem. So this now sounds a little bit complex, but to make it short, my research question from the start was, to what extent can the wet snow problem be determined with openAMUNDSEN? In the next couple of minutes, I will give you a short introduction to my topic. I will present you some of the methods I use and point out to the most important results, and also give you a short outlook into what's possible with these results in the future. I think everyone in this room is aware about the wet snow avalanche problem, but just to remember for everybody, the weakening of the snow cover on the wet avalanche problem is due to liquid water. And this liquid water is either caused by rain or melt. So the question here now is how to capture this liquid water in the snowpack. And there is this measure called the liquid water content, and it's kind of a challenge to measure it. So there are point measurements, for example, with the snowpack analyzer to conduct a point measurement, but on a spatially distributed area, it's quite challenging to get accurate measurements. So scientists thought about remote sensing. So there are ways to do a spatially distributed measurement in this case, but it's only detecting the reflection of the surface, so there's no information about the entire snowpack. And this is actually where openAMUNDSEN has a great advantage, because the snow simulations of this model provide a spatially distributed liquid water content, and you can use future data, but as well as look into the historical data. Here is a short idea of what openAMUNDSEN, the physically based snowpack model, is about. So you need as input data weather station data and a DEM, and then this is necessary for the model to run. And as an output, you get for each grid cell a value for each time step. So I used a 100-meter spatial resolution and a 3-hourly temporal resolution, but you can also use a 1-hourly time step or like a daily time step. My research was focusing on 2 warning regions defined by the Avalanche Warning Service Tyrol in Osttirol, which is south of the main Alpine ridge. And the 2 warning regions are called DefereggerAlps and Schober Mountains. In the second map, you can see the blue dots, and these are representing my weather stations that I used as an input. And here are 2 of the methods I used. So I did a comparison of the average liquid water content with the forecasted wet snow problem. And I also did a visual comparison of snow simulation output, remote sensing data, and the avalanche forecast. And here I come to the results. So here you can see the average liquid water content in blue for the DefereggerAlps in the season 20 and 21. So it's a seasonal development, and in the gray bars show the days where the wet snow avalanche was announced by the avalanche forecast. And this is actually quite a good result because you can see there's an increase in liquid water content, which is combined with an announcement of the wet snow avalanche problem. And as you might know, as soon as liquid water infiltrates into the snowpack, the weakness of the snowpack starts. So this is actually where the situation of wet snow avalanches can occur. So, for example, when it stagnates here in March at the end, it's actually stabilizing again. So this picture of the development of the liquid water content is actually a very satisfying result. As a next step, I took a couple of days to look deeper into the spatial distribution of the liquid water content output. And on that day, April 20th in 2022, rain was the main cause of the wet avalanche problem. And just like the rain was not in high elevations, so only in lower elevations. So I will then go more into detail with each plot, but this is just for background information. And I compared like satellite data, the model output, and the danger level of the avalanche forecast to each other. I will now start to introduce you the each grid. So here you can see the output of openAMUNDSEN. The blue areas are very high values of liquid water where the snowpack was affected by the rain. The yellow and green areas are not affected by the rain because they are in higher elevations. And the gray area is a no snow area, so no snow was existing there. This can be compared to the Sentinel-1 data I got from the Alp Snow project. And here the interesting pattern is the black area because this simulates the wet snow area. This has to be interpreted very cautiously because the green areas are forest, and where there's forest, there's no information about the snow. So there's kind of a lack of knowledge there. And here for another comparison, there's the danger level of the Avalanche Warning Service Tyrol. The yellow areas represent a moderate likelihood of wet snow avalanche occurrence, and the green area shows a low probability of that. I used this last map and the simulation output to facilitate the information because I thought it might be easier to get the information at one glance. So there's this threshold value of 3 volume% of liquid water, and above this value, it's more likely that wet snow avalanche activity occurs. So this area is colored in yellow and can be seen at the first glance. The green areas show values that are lower than 3 volume% of the liquid water content. So if you want to have information about where exactly the wet snow avalanche occurs, you can immediately see it at one glance where you need to look more in detail into the snowpack. If you compare all those four plots, you can see that the areas where wet snow avalanches should occur basically match, and this is actually a quite satisfying result for the simulations with openAMUNDSEN. So my take-home messages are that the simulation of the spatio-temporal dynamics of the liquid water content with openAMUNDSEN work quite well. It's possible to identify areas with high values of liquid water content. So therefore, we can give some indication of a wet snow problem, spatially and temporally distributed, which is quite a good result in the end. So with this result, there's some options for the future. You can transfer this into an operational process and maybe somehow then contribute to the avalanche forecast operations. So I'm at the end of my presentation. I'm happy to answer your questions now. And if you want to further reach out, you can contact me at my email address.
Andrea, are there already some questions here? No questions here. Let's look at the chat. So you mentioned the liquid water content, if it's above 3%, this is a threshold for you to decide whether we would have a wet snow problem or not. Is this liquid water content for the entire snowpack, or is it for certain layers within the snowpack, or how does that work?
It's actually the liquid water content for the entire snowpack. As openAMUNDSEN doesn't have a layer stratigraphy in its model run, it's like the whole liquid water content of the snowpack.
Okay, and if we only have a wettening of the upper part of the snowpack, which would lead to avalanche activity, would we see that in, let's say, in high winter and we have a rain event and we have just the upper snowpack which gets saturated with water and we will see avalanche activity? Would you be able to see that somehow within this modeling?
Yes, can I still? So this is like the layers openAMUNDSEN has. It has like 3 multi-layers. And they are empirically there. So you would see then rise in the first and in the second layer if it's just in the upper part of the snowpack there. So you could track that with this graph, but there's not really a chance to look right into a certain layer with this model. This is a weakness of the model, but as I was saying, the focus is just to get an information where to look more into depth into the snowpack. So it would give you an idea of where you need to look into, for example, snowpack analysis.
Okay. Last question from my side. How does the model differentiate these different layers?
It's an empirical process with snow height and snow density. So there is not with new snow or old snow, it's just an empirical build-up of like 3 layers here in openAMUNDSEN, 3 layers. And it's based, like I said here, on the FSM model from Esri. So, yes.
Okay, I think we have a question in the chat too. Did you compare measured and modeled snow heights in the area? That was the question of Sasha Belair.
At the first start, I did a point simulation at a certain weather station to compare temperature, snow height, and the snow equivalent, just to get an idea if the liquid water content development also makes sense in comparison to those values. But I did not actually compare measurement and point simulation because like we focus on a spatially distributed area, not on a point, and this measurement on a spatially distributed area is actually not accurately possible at the moment right now.
All right. Okay, thank you very much. This is for you. And again, an applause for Andrea. Anything else come up?
Und dann wieder eine Frage, müssen wir aus dem Bereich nach hier, oder?
Ja,
Oder zwischen.
So, also, die nächste Vortragende, our next presenter is Marie Schroeder. Marie did her entire career at the University of Innsbruck. So she started bachelor and master at the Institute of Atmospheric and Cryospheric Sciences. And we are happy to have you here. And I'm really interested and curious on what you have to present. Marie, go for it.
Yes. Okay, so thanks a lot for this nice introduction. I'm very happy to be here and to present to you the results that I did in the framework of my master thesis about measuring snow water equivalent with a cosmic ray neutron sensor in the fashion of, we did a case study on Hintereisferner, a glacier here in Austria. But before going into more detail what cosmic ray neutron sensor is and what we exactly try to answer with it, I want to give a short introduction why we actually care about snow water equivalent in general and especially in high mountain areas and on glaciers. So looking at the snow water equivalent measurement network, we can see on the right side a plot of automatic weather stations across Europe, where the important word here lies with automatic, so stations that measure automatically in daily or sub-daily timestamps. And we can see just comparing snow depth and snow water equivalent stations here that we have about 20 times more snow depth stations and very few snow water equivalent measurements. And then looking only at the yellow part, which are only stations above 2,000 meters, the picture gets even worse, so to say, for snow water equivalent, as there are only 36 stations across all of Europe that measure snow water equivalent automatically. So we can generally see that we have a bias towards lower altitude and also latitudes, and the network is just really sparse, which leads to an inadequate representation of the snow variability, especially in these high mountain areas. And therefore, you could kind of conclude that there is the need for a reliable automatic measurement technique here. And so we decided to test one method that could be promising for this, which is the so-called Cosmic Ray Neutron Sensor. This is what the Cosmic Ray Neutron Sensor looks like. It's just a big white tube, and what it does, it can count the neutrons that are freely available in the atmosphere. And so these neutrons come from so-called galactic cosmic waves, which are protons. And when they have enough energy to penetrate the electromagnetic field of the Earth, they can enter the atmosphere. And then in the atmosphere, a cascade of reactions happen between protons and different molecules. And one of the end products are so-called fast neutrons. And these fast neutrons are exactly what our sensor can measure. And so how do we measure snow water equivalent with this now? Is that these neutrons are highly moderated by hydrogen. And so if we imagine, like on my picture, the sensor is placed on the glacier, or in this conceptual picture on the grass, and the snowpack accumulates over the winter, less and less neutrons can reach the sensor, and this decrease in neutron counts we can relate back to snow water equivalent. And so, as I said, we did a case study on Hintereisferner with this sensor, which is a glacier at the end of the Ötztal Valley here in Tyrol. And here you can see a bit of an overview of the valley, and zooming a bit more into the glacier. Our station was located where the big orange star is at about 3,000 meters on a small plateau on the glacier. And so this is what the weather station looks like. We had a bunch of atmospheric measurements, and most importantly for my analysis, the snow depth measurement and of course the neutron sensor. But additionally to this automatic measurement, I did 10 manual measurements over the winter 21-22 to have a comparison between automatic and manual measurement. And so this leads me straight into the first research question, the first question I try to answer, which is, how does the neutron sensor perform compared to the manual field measurements that we kind of take as accepted and the truth in this comparison. And so looking at these results, in blue, we can see the daily neutron sensor, or the snow equivalent from the neutron sensor, and in purple, the manual field measurements. And generally, we see quite a good agreement within the respective error estimates, with also a good mean absolute error of 37 millimeters water equivalent. And now the question was, having now this daily time series snow equivalent, what questions can we answer with this? And so one question we came up with is that what is the comparative performance of different snow models when comparing it to our measurement of the neutron sensor? And for that, we chose two snow models, the first one being snowpack, which is a physically based snowpack and ground surface model, which needs different meteorological input data to do a simulation. And on the other hand, we chose delta snow, which is a semi-empirical model, therefore solving different parts empirically and only needing snow depth as an input variable. So for us as the user, the main difference would be that for snowpack, we need more input variables than for delta snow that only needs snow depth. And so looking at the results from these two model ones, we can see that both generally perform quite well, with green here being snowpack and orange delta snow. We have a slight underestimation of both models, but generally they also show good mean absolute errors in comparison. But we can see that snowpack at peak snow equivalent captures this peak quite well, whereas delta snow kind of misses this peak and underestimates the maximum snow equivalent. But generally, looking at that we only give snow depth to delta snow and the rest it's solving internally, we still see really good performance from this model. And so moving on from here to a totally different question that I try to answer, which is if it is possible to determine scaling factors from various stations surrounding Hintereisferner to scale snow equivalent estimates to the glacier. And so what this exactly means is that here we see the overview of the Rofental again, and we chose 4 weather stations at different altitudes. And the idea of this precipitation scaling is to deduce a scaling factor from these weather stations to provide an estimate of snow equivalent on the glacier over the winter, and in best case, at some point, not needing the measurement at the glacier anymore and just being able to scale from the measurement from these stations. And so the first thing we needed to deal with is that these stations don't measure snow equivalent, but they all measure precipitation. So the workaround I chose is that I approximate snow equivalent with accumulating precipitation over the accumulation phase of the winter. And so how did I do this scaling? Now, what do I exactly mean? It's actually a really simple linear relation that I try to find between the snow equivalent on Hintereisferner and the snow equivalent at the stations. So I try for each station to find this factor C. And looking at the results, so here we can see in the solid lines, the 4 different stations, and in the blue line, the measurement from the neutron sensor. And so what I try is just to find a factor by which I need to multiply these, each of the solid lines to make it match the blue measurement. And I will show you the thought process, how I approach this for the Hintereis station, which is the highest station, but I did exactly the same thing for the 4 stations in the end. So as I said, the first part was finding this linear relation. So we see on the x-axis the snow equivalent measured at the Hintereis station, and on the y-axis the measured snow equivalent from the neutron sensor, and then the linear fit. And what you can kind of see obviously is that we have this overestimation of our fit in low snow equivalents, and then we kind of shift into an underestimation. And looking a bit more into this, where this comes from, it became kind of clear that it was one specific snow event, a big snow event in the beginning of February that led to this weird behavior of our fit, because it was quite poorly captured by the automatic weather station in the precipitation data. And so I started thinking how I can work around this, and the idea came to introduce a step function that you can see in the orange line on the right plot. So what I try is to find a linear fit for both of these regions without taking into account the step in the middle. And so this process I repeated for the 4 stations. So first I look to find a linear fit for each station, and then I try to find a step function fit. And then at this point, I already had data from another winter, so I could test on unseen data how these scaling factors actually work now on new data. And so it came out that for some stations, the linear fit worked better, and for other stations, the step function fit works better. So generally, the conclusion from this analysis I got was that we would need more winters of data to really find a solid scaling factor, that we get more variability in our fitting process, so that we can also confidently then use this scaling factor on future winters. And so this brings me to my last slide, a short summary. So my main conclusions from this work were that we successfully could capture reliably and effectively snow Earth equivalent with the neutron sensor over this winter and still continuing now. We could show that both the snow models could approximate snow Earth equivalent quite good. And we could deduce scaling factors from 4 weather stations with different methods, but coming to the main conclusion that we need more data to really make the scaling solid and reliable. And with that, thank you a lot for your attention, and I take any questions if you have any.
Interesting. Thanks, Maria. Your time. Can you come just to one of the microphones so also the virtual persons can hear you?
Sure. Where are they? Yes, here.
Weird. Thank you for the presentation. Was really interesting. One question that I would have for the data fitting.
Yeah.
Did you, like, the point along the x-axis where you choose that the step happens?
Yeah.
Is that a model parameter, or did you kind of choose by eye sort of where one linear thing starts and then the other one?
No, it was kind of a mixture of both. I gave the model kind of a rough estimate of where I see visually where the step would be, but then I used a model algorithm that like tried different possible steps. And then I looked which gave me the best fit or like the lowest error. And that one I chose. So it was kind of me choosing it first, but then letting the model fine tune the position of the step.
Okay. Thank you.
Great, thanks. Is there something on the web? Nope.
Just a short question about the measurements.
Yeah.
Because I think you probably measured them in a flat area or flat terrain.
Yeah. Yeah.
You know, is it possible also install this in like a steep slope to measure the snow water equivalent?
According to the manufacturer, yes, it's possible, because the neutron sensor basically sees 360 degrees, so it sees the whole water equivalent that is around it. So, and kind of the theory behind it is that once a snowpack is big enough, you can kind of see it as a column measurement. So I would also say that you can put it in a steeper slope, and then you would have kind of the column that is of the neutron sensor. Yeah.
Thank you.
Time for one last one. And I do the last one.
Yeah.
So we had one measurement and one scaling question, now one modeling question. What do you think is the reason of the different results for the 2 different models, especially towards high peak SWE periods?
Yeah.
Delta snow underperforms there.
Yeah.
And snowpack performs better. What is the main reason for that?
So there's one really good reason, if I find the right slide. Yes. So one reason is, firstly, that delta snow was calibrated on 6 stations over 14 years, but you see between 590 and 1,650 50 meters. So really not for the elevation band we are in, but this was also kind of the intention to test if it is also working on the glacier. But then the main reason for this, you could see in the plot that it really kind of plateaued at some point, is that internally the model sets maximum density at 400. And this is just too low for what we measure on the glacier. I also did the whole analysis for density, and there you can really see that our density rises up to 500 or a bit higher, and the delta snow just stops at 400 as it is set at maximum 400. So I think that if you would tune the model a bit and allowing it higher densities, that you could probably optimize the performance of delta snow quite a bit and make it, yeah, probably even closer to what we measure.
Thank you very much. So Marie, very nice talk. Just you our full cup for the next coffee or tea break.
Thanks.
And thanks for having presented your results with us here. Yeah, there is one more.
How expensive is the sensor? Rainer bought it, so I don't know.
It was for free.
For me, yes.
So the sensor is about order of magnitude 10,000 euros, but just the sensor alone without data logger, and you need some additional measurements. For example, you need a hygrometer because you also need to know the humidity in the air, because there are also the neutrons modulated by the hydrogen in the air. So,
yeah.
Cool.
Thank you.
Then we move on to our last speaker, Paula Spannring. Paula is also with her career, or has also started with her career at the University of Innsbruck, again in atmospheric and cryospheric sciences. You are now with BFW for your master thesis in collaboration with the Avalanche Warning Service and with the university. And Paula is now searching for jobs, so everyone has opportunities. Listen to Paula.
Thanks, Christoph. Okay, I guess the most of you are already planning the next ski tours, and probably the most used these maps with the slope inclination for the planning. And I will show you now two other maps which contain more avalanche characteristics and classify the avalanche terrain. One is the Avalanche Terrain Exposure Scale, ATAS, and the other one classified avalanche terrain, CAT. And I don't just want to show you nice, colorful maps. I also want to compare both methods. So first of all, both maps, ATAS and CAT, are static maps. They only consider the terrain and not the current avalanche danger situation. And both can be computed by an automated workflow, which consider medium and large avalanches, which are typically triggered by skiers. So ATAS and CAT are helpful tools for planning a ski tour or a professional trip. So what is ATAS, the Avalanche Terrain Exposure Scale? It classifies the terrain in 4 classes. One is the simple. It's, for example, at Birgitsköpfe, where there is low angle and forested terrain. Challenging is the second class. It's, for example, at Guildford, where there are well-defined avalanche paths and release areas. Complex terrain is defined as open and steep slopes, for example, at Zischgeles. And extreme terrain are very steep slopes with couloirs, cliffs, for example, at Treuhengrad and Rotkogel. So, and how can you compute the ATAS maps? As I said, it can be computed by an automated workflow, and it needs 2 input data marked in blue and 3 computational tools marked in yellow. The input data are a digital elevation model and a forest layer, which contains forest density. And with those input data, we can compute potential release areas and the corresponding avalanche runout. The runout is computed by FlowPy, which is quite a simple avalanche simulation tool based on a geometrical concept, which means that there is an alpha angle between the horizontal and a line through the release point and the deposition point. And this alpha angle is set to a specific value, in this case to 26 degrees. And depending on that angle, the deposition point is computed by FlowPy. And yes, I can count, there's a third computational tool, the classifier. And it combines the slope inclination, forest density, potential release areas, and the avalanche runout to the 4 artist classes. So now to the second map, the classified avalanche terrain. The cut map delineates potential release areas, areas where remote triggering is likely, and very steep terrain. And all cut maps, which I will show you now, are computed by the SLF in Davos. And how do they compute the maps? They also need 2 input data and 3 computational tools. The input data are a digital elevation model and a forest layer again. And they also compute potential release areas, but with a different algorithm than in the ATLAS workflow. And they also differentiate the potential in very low, colored in light red, to high, colored in dark red. The avalanche runout is computed by RAMS, and additionally, areas where remote triggering is likely are computed, and also the potential is differentiated from low, colored in light blue, to high, colored in dark blue. And those potential release areas, the avalanche runout, and the areas where remote triggering is likely are colored together with very steep terrain, which is steeper than 50 degrees in the cut map. So now we have 2 nice colorful maps, and let's compare them. I compared them in a test region in Zell-Rhein. The area is around 100 square kilometers large. And let's start with the simplest case, ATLAS class simple. This bar means that 90% of the area which is assigned to ATLAS class simple has no category in the cut map. So there's no potential release area, no avalanche runout, no potential remote triggering. For example, here, we are here around Pforzheimer Hütte in Zell-Rhein. I guess that most of you know the area, it's quite a popular ski touring area. And in the northeast of Zwieselbacher Rosskuhl, here, the ATLAS class is simple and challenging. And in the same area, in the cut map, there is no classification, except the small challenging part has a low potential in release area and remote triggering. Now to the extreme case. This bar means that 60% of the area which is assigned to ATLAS class extreme is in the cut map assigned to very steep terrain, and the other 40% are assigned to release areas with a high potential. For example, here. The ATLAS map shows in this part as purple and red, which means there is extreme and complex terrain. In the cut map, the area is assigned to very steep terrain and release areas with a high potential, colored in dark red. The ATLAS class complex. This bar looks quite colorful, and which means that the ATLAS class complex actually contains all cut categories, from no classification to very steep terrain. Which means that dealing with that ATLAS class complex is quite challenging. For example, in this area, the ATLAS map is shows complex and challenging terrain. In the same area in the cut map, there is, a bit surprisingly, no classification. So when concluding the comparison of artist and cut, there's no real true or wrong and no better or worse. But I would suggest for a user who wants to use a map, when using a cut map, it's necessary to know what is a release area and what is remote triggering. And on the other side, when using a cut map, actually there is no previous knowledge necessary. And for a small conclusion of the comparison before, in areas where ARTAS is simple, in the most areas in the cut map, there is no classification. And in areas where ARTAS class extreme, mostly the cut shows a very steep terrain. So now we compared the end products of ARTAS and cut, but I also want to compare the intermediate steps of both methods, especially the avalanche runout. And here is the runout of the cut map, colored in yellow. And this is the runout simulated with FlowPy, with this release area. I can put it again. And I guess you see a difference in both runouts. And I want to analyze what are the consequences of the differences in the runout for the ARTAS maps? And is it necessary maybe to use a bit more complex avalanche simulation tools for the ARTAS workflow? Thanks. And are there any questions?
Thank you, Paula. Very nice. There is one question on the web. Which map is used by Shitonguru?
Shitonguru uses kind of ARTAS map, but so he or they do. Yeah, it's they also classify the terrain in more or less 4 classes, but they use different parameter to a bit modified parameter to calculate the maps.
Thanks, and Rainer here.
Are both classifications based on the same DM, or do they use different?
The ARTAS map is based on a 10-meter DM, and the cut map on a 5-meter DM.
But it's from the same time period, and do they also use different information from the DMs, so just slope or also aspect or the rain roughness or whatever you can?
They also consider the curvature of the terrain, but not the aspect and also not the elevation. But actually, the more or less the same parameter.
Then there is another question on the web. When would ARTAS maps be available in Tyrol, Austria?
I think that's a question for you, Christoph.
As soon as we have the money for it. Maybe one last question here in the room.
Maybe I have one. Where do you personally see the advantage of like the ARTAS maps compared to the cut, or the other way around?
Stop. Come forward.
Hello. So Paula, thanks for the presentation. And where do you personally see the advantages of ARTAS or cut, or the disadvantages?
So one advantage is of ARTAS that all the computational tools are open source, which is not in the cut map. And as I said, the ARTAS map does not, or there is no previous knowledge necessary. So if very beginner wants to use a map and wants to go the first ski tour, actually he does not know what is a release area and what is remote triggering. And then an artist map is quite useful when he just says he wants to stay in maybe simple and challenging terrain. But if, I guess, for example, the most of you, if you know what is a release area and what is remote triggering, the cut map gives more detailed information. And yeah, if you know there is no high danger of potential or no high danger of remote triggering, it's enough maybe to stay in terrain where or you don't need to consider the remote triggering areas.
All right. Thank you, Paula, for your presentation. Also, Open Cup for you.
Thank you.
Thank you very much. We are not at the end yet. First, an applause for Paula. We are not at the end yet because it's your time now to shine. Please vote. So every one of you, also bitte jeder von euch, der was dazu geguckt hat, nehmt euch bitte eine halbe Minute Zeit, um den Review zu machen, damit wir danach eine Grundlage haben, eine vernünftige Entscheidung zu treffen zwischen den drei sehr, sehr guten Präsentierenden.
In der Tat, also es ist wirklich die Qual der Wahl. Es waren alle extrem gut. Es hat mich gefreut, dass ihr eure Ergebnisse hier uns präsentieren habt können und war ein wirklich extrem interessantes Themengebiet. Also von Schneewasserwert bis bunten Karten über Nachtschneelawinen, alles dabei. Hat mir extrem gut gefallen.
Christoph, wann haben wir das nächste Seminar?
Das nächste Seminar findet am 4. März statt, wieder um 12 Uhr hier. Das Thema wird dieses Mal auch um Schneemessungen sich drehen, und zwar um Radargeräte Schneemessungen. Eine alte Größe dieses Businesses grabt seine Präsentation raus. Achim Heilig wird uns einige Sachen zu diesem Thema zeigen, wo die Vorteile, wo die Nachteile, wo die Herausforderungen an diese Messmethode für Schnee, Eis und Lawinen ist.
Ja, sehr gut. In diesem Sinne werden wir jetzt still und leise die Präsentation beenden. Jeder darf noch fertig machen, bevor wir uns wieder in Interaktion begeben, hier im BFW oder wieder zurück an den Arbeitsplatz müssen. Vielen Dank an alle, die was online dabei waren. Natürlich die, was in Präsenz dabei waren. Vielen Dank fürs Voting, und in den nächsten Tagen gibt es von uns News
Genau.
zu den Gewinnern und
Also die Gewinnerinnen. Und diese News verbreiten wir natürlich über unseren Newsletter. Also wer sich noch nicht eingeschrieben hat bei unserem Newsletter und total neugierig ist, wer das jetzt wird, der muss sich natürlich leider einschreiben.
Und alle anderen natürlich
auch. Genau. Dann vielen Dank auch nochmal an die Präsentierenden. Das war extrem cool, extrem schöne Sache, und wir sehen uns hoffentlich bald wieder. Ciao, macht es gut.
Servus.